In December 2021, NASA launched the most powerful space telescope ever built. It was supposed to confirm what scientists already knew about how the universe began. It did the opposite. The James Webb Space Telescope has been sending back images of galaxies that should not exist. Galaxies that are fully formed, massive, and burning with hundreds of millions of stars at a point in time when the standard model of cosmology says there hadn't been enough time to build them. And separately, the universe is expanding faster than every calculation says it should be. And two independent telescopes have now confirmed the same impossible number. These are not fringe claims. They are published results from peer-reviewed journals, confirmed by Nobel laureates, and debated at physics conferences as of 2025. Something about the standard picture of cosmic origins is incomplete, and the images coming back from Webb are forcing the question that cosmology has spent decades trying not to ask. What was there before the Big Bang? What the Big Bang actually says? The universe is 13.8 billion years old. That number comes from two separate methods of measurement that agree with each other to a high degree of precision, and it is one of the most well-confirmed figures in all of science. The Big Bang was not an explosion in space. It was the expansion of space itself. Before it, the current laws of physics break down at what scientists call a singularity, a point of infinite density and temperature, where the equations stop producing meaningful answers. The theory does not describe what came before, because, in the standard model, time itself began at the Big Bang. Before it, the concept of before may not apply. About 380,000 years after the Big Bang, the universe had cooled enough for the first atoms to form. When that happened, light could finally travel freely for the first time. That light is still traveling today, filling the entire sky as a faint glow of microwave radiation called the cosmic microwave background, known as the CMB. It sits at just 2.7 degrees above absolute zero. Turn a television to a dead channel, and a small fraction of that static is the leftover radiation from the birth of the universe. The CMB is the oldest light we can observe, a snapshot of the universe when it was 380,000 years old, and it has been mapped in extraordinary detail by NASA's WMAP satellite and the European Space Agency's Planck Observatory. The standard model built from all this data predicted what the early universe should look like. Small structures first, simple chemistry, galaxies that grew slowly over hundreds of millions of years from the gradual pull of gravity on clouds of hydrogen and helium. Webb was designed to see exactly that period. What it found instead prompted a scientist at the JADES research program to get up from his chair, walk down the hallway, and look at the faces of his colleagues because he could not believe the data he was reading. The galaxies that should not exist. In October 2023 and January 2024, astronomers used the James Webb Space Telescope to observe galaxies as part of the JWST Advanced Deep Extragalactic Survey, known as JADES. Using Webb's near-infrared spectrograph, the team observed a galaxy called JADES GS Z14-0 for nearly 10 hours. The spectrum came back unambiguous. This galaxy existed 290 million years after the Big Bang, making it the most distant galaxy ever confirmed by direct spectroscopic measurement. The universe was only about 2% of its current age. The galaxy is over 1,600 light years across. It is producing hundreds of millions of solar masses worth of stars. It contains heavy elements, which means multiple generations of stars had already lived, died, and scattered their material before this galaxy was observed. researcher Kevin Hainline described his reaction when the data was confirmed. He said it just seemed too big and too bright, and that it should not be there. The Standard Model predicted that galaxies at this early stage should be small, dim, and made mostly of hydrogen and helium, the only elements produced in the Big Bang itself. Heavy elements like carbon and oxygen require stars to forge them through nuclear fusion and then explode to spread them. Getting from a universe with no stars to a galaxy containing multiple generations of stars producing detectable heavy element signatures takes time. The model said that galaxies should not have had that time. Jade's GS-Z14-0 is not an isolated case. A 2023 paper in the Astrophysical Journal identified 6 of the earliest and most massive galaxy candidates observed by Webb that appeared to have converted nearly 100% of their available gas into stars, a finding that multiple research teams described as inconsistent with the prevailing model. The large number of unexpectedly bright, massive, and structurally mature galaxies at the extreme edge of the observable universe appeared in Webb data so consistently across independent surveys that by 2025, peer-reviewed papers were citing it as a systematic challenge to standard galaxy formation theory. Some researchers proposed that bursts of rapid star formation could explain the brightness without requiring changes to the underlying cosmological model. Others pointed to the possibility that massive black holes in these early galaxies were contributing to the observed brightness. Those explanations resolve parts of the problem. None of them fully accounts for the heavy element content of Jade's GS-Z14-0 at 290 million years after the Big Bang. The galaxy carries chemical signatures of a history that does not fit inside the time available under the Standard Model. The data does not require tearing the model apart. It does require explaining something the model did not predict. And the early galaxy problem is only one of 2 measurements currently causing genuine crisis-level concern in cosmology. The second one involves the speed of the universe itself, and 2 of NASA's most powerful telescopes spent years trying to prove it was a measurement error before confirming it was not. The universe is expanding at the wrong speed. In 1998, astronomers discovered that the universe is not just expanding, it is accelerating. Something is pushing everything apart faster and faster. That something was named dark energy, and it makes up approximately 68% of everything in the universe according to measurements from the Planck satellite. No one knows what it is. That discovery changed cosmology permanently. The problem in 2025 is that the expansion rate itself is producing 2 different numbers depending on how you measure it, and the gap between those numbers has now exceeded 6 statistical sigma. In physics, 5 sigma is the threshold for calling something a confirmed discovery. 6 sigma is not measurement error. 6 sigma is a problem with the model. The expansion rate of the universe is called the Hubble constant. When astronomers measure it using the cosmic microwave background, the oldest light in the universe, they get a value of approximately 67 to 68 kilometers per second per megaparsec. When they measure it using nearby supernovae and the distance ladder of the current universe, they consistently get approximately 73 kilometers per second per megaparsec. These 2 numbers should match. They do not. In 2024, the James Webb Space Telescope was used to observe the same distant stars used to calibrate the local measurement to check whether the Hubble Space Telescope had made an error. Webb confirmed the Hubble data. Nobel laureate Adam Riess of Johns Hopkins University, who led that analysis, stated that with 2 NASA flagship telescopes now confirming each other's findings, the problem has to be taken seriously. It represents a challenge and an opportunity to learn more about the universe. a January 2025 paper in the Astrophysical Journal. Letters by a team from Duke University used an independent method, comparing distances to the Coma cluster using data from the Dark Energy Spectroscopic Instrument, and found results consistent with the faster local measurement. The lead author, Daniel Skolnick, stated directly that the model of cosmology might be broken. Before we move on, if you're enjoying this analysis, please consider subscribing. It helps the channel tremendously. As of late 2025, the Hubble tension stands at more than 6 sigma. The standard model of cosmology predicts one expansion rate. The universe is running at a different one. Both the early galaxy problem and the expansion rate problem point to the same conclusion. Something in the earliest moments of the universe, or possibly before it, is not accounted for in the current picture. What could have come before? The question of what existed before the Big Bang is not science fiction. It is an active area of theoretical physics with multiple competing models, each making specific predictions about what we should be able to detect if they are correct. The leading framework in standard cosmology is cosmic inflation. In this model, the universe underwent an extraordinarily rapid expansion in the first fractions of a second after the Big Bang, expanding by a factor of at least 10 to the 27th power before slowing into the expansion we observe today. Inflation explains why the observable universe looks nearly identical in every direction, why it is geometrically flat, and why the CMB temperature variations are the size they are. The quantum fluctuations produced during inflation seeded the density differences that eventually became every galaxy, star, and planet. But inflation does not explain what came before it or what caused it. And the Big Bang itself sits at a mathematical singularity where physics cannot reach. This is not a gap in our knowledge to be filled eventually. It is a hard boundary in the equations. Oxford mathematician and Nobel laureate Roger Penrose has proposed a model called conformal cyclic cosmology, or CCC, in which our universe is one stage in an eternal sequence of cosmic cycles he calls eons. In this model, the Big Bang was not the beginning of everything. It was a transition point. The previous eon would have begun with its own Big Bang, expanded, formed stars and galaxies and black holes, and eventually reached a state of maximum expansion, where all matter had decayed and all black holes had evaporated through Hawking radiation. At that point, Penrose argues, the mathematical structure of the dying universe maps onto the birth conditions of the next one. The model makes a testable prediction. When supermassive black holes in the previous eon evaporated through Hawking radiation, that process would have released energy concentrated at specific points in space. Those points of energy, stretched enormously by the transition to our aeon, should show up in the cosmic microwave background as circular spots of slightly elevated temperature. Penrose calls these Hawking points. In 2020, he and collaborators published analysis in the monthly notices of the Royal Astronomical Society, claiming to have found such spots in both the Planck and WMAP satellite data at 99.98% confidence. Other researchers examined the same data and concluded the spots did not exceed expected statistical noise. A 2024 reanalysis found no statistically significant evidence for Hawking points using updated Planck data. An August 2025 preprint argued the analysis had been conducted incorrectly and that the CCC signal remains present. The debate is ongoing in the active scientific literature. A separate framework called the Big Bounce proposes that the Big Bang was a rebound. A previous universe contracted under gravity to an extreme density, then bounced outward rather than collapsing to a true singularity. Loop quantum gravity, an approach to combining quantum mechanics with general relativity, produces this outcome mathematically. In this picture, there was a universe before ours. It simply compressed to a state of extreme density and then became our expansion. Eternal inflation proposes that the rapid inflation that followed our Big Bang never actually stopped everywhere. While it ended in our region of space, it may still be ongoing in others, producing new bubble universes continuously. Our Big Bang was one bubble forming inside a larger, eternally inflating space. Other bubbles would represent other universes, potentially with different physical constants. There is currently no way to observe outside our bubble, so this model cannot be directly tested. What all these models have in common is that they treat the Big Bang as an event within a larger structure rather than the absolute beginning of everything. The singularity in the standard model is not a description of what happened. It is the place where the equations stop working and something else must take over. What the data adds up to. The James Webb Space Telescope has now operated for over 3 years. In that time, it has found the most distant galaxy ever confirmed, identified a population of early galaxies with properties that challenge the timing predictions of the standard model, and confirmed that the Hubble tension is not a measurement error. Those are 3 separate observational results, each with their own published literature and independent confirmation. None of them prove that something existed before the Big Bang. What they do is push the standard model to its edges and reveal that it is incomplete. The model predicts a slower expansion. The universe runs faster. The model predicts small, simple, early galaxies. Webb keeps finding large, complex ones. These are not philosophical puzzles. They are numbers that do not agree. The Hubble tension, exceeding 6 sigma as of 2025, is the more statistically clean problem. At that significance level, the standard explanation that the measurements themselves contain errors becomes untenable. Researchers at the 2025 Tensions in Cosmology conference in Corfu described the discrepancy as no longer a peripheral curiosity, but a central, data-driven challenge to the concordance model of cosmology. The early galaxy problem is more ambiguous, because some of the initial mass estimates for early JWST galaxies were revised downward after more detailed analysis. A 2024 study from the University of Texas found that some of the most extreme early galaxy candidates were less massive than first reported when the contribution of black holes to their brightness was properly accounted for. The field is still sorting through which anomalies are measurement artifacts and which are genuine challenges to the timeline. What remains after that sorting is still significant. JADE's GSZ 14-0 is confirmed. Its redshift is spectroscopically measured. Its heavy element content is real. It exists at a point in cosmic history where the standard model did not predict it could have the properties it has. The before Big Bang models make predictions that can be tested. Hawking points, gravitational wave signatures from a previous cycle, specific patterns in the cosmic microwave background, polarization that inflation alone cannot produce. The next generation of cosmic microwave background observatories and gravitational wave detectors will either find those signals or rule them out. The data right now sits in the gap between what the model predicts and what the universe is doing. That gap is not closed. It is widening with every new image Webb sends back. Verdict: the James Webb Space Telescope found a galaxy that is fully formed, chemically complex, and blazing with stars 290 million years after the Big Bang. The standard model did not predict it could exist there. The universe is also expanding 6 sigma faster than the same model says it should be. 2 independent NASA telescopes confirmed the same number. These are not broken theories. They are incomplete ones. The Big Bang happened. The evidence for it is overwhelming and uncontested. What happened before it, or what caused it, is a question the current model cannot answer, because it was never designed to. The CMB carries imprints from the first 380,000 years. What came before those 380,000 years is hidden behind a wall of heat and density the light cannot pierce. Penrose thinks his cyclic universe left marks on that wall. Loop quantum gravity says the universe bounced from a previous one. Eternal inflation says our Big Bang was one bubble in a foam of universes that never stops expanding. None of these are confirmed. All of them are testable, and Webb is still sending images back that the model did not predict. The question of what came before is not answered. It is being asked more seriously now than at any point in the history of cosmology. If you enjoyed this video, make sure to subscribe. Thanks for watching, and we'll see you in the next one.